Dear Dean of our faculty, our Vice Deans, academics, researchers, students, and guests. Good afternoon and welcome. My name is Merve Ertok Onurlu. I'm working as an assistant professor at Department of Econometrics at BIGA Faculty of Economics and Administrative Sciences. So today we have all gathered for the webinar series of our faculty at Çanakkale 18 Mart University. Professor Dr. Myoung-jae Lee from Korea University at the Department of Economics will deliver a presentation for today. And we would like to express our sincere thanks to Professor Lee for kindly accepting our invitation for the seminar. Professor Lee, it's a tremendous delight and honor for us to have you participate in our faculty seminar series. We would also like to acknowledge the Dean of our faculty, Professor Dr. Ercan Sarıdoğan, and Professor Dr. Ebru Çağlayan Akay from Marmara University, Department of Econometrics, for their tremendous efforts and cooperation in making this seminar possible at this very precise moment. We would like to thank everyone for taking the time to be with us today and hopefully contributing to the accomplishment of this event. Before I provide a very brief introduction about Professor Lee, I would like to give the floor to the Dean of our faculty, Professor Dr. Ercan Sarıdoğan, to make his speech. Dear Dean, the floor is yours. Thank you.
Teşekkürler hocam. Değerli konuğumuz Profesör Lee, değerli hocalarımız ve kıymetli katılımcılar, hepinizi saygıyla selamlıyorum. Ekonometri bölümümüzden Doktor Öğretim Üyesi Merve Ertok Onurlu hocamız öncülüğünde organize edilen bu webinere hepiniz hoş geldiniz. Seminere katılımıyla fakültemizi onurlandıran Profesör Lee'ye şükranlarımızı sunuyorum. Kendisini her zaman fakültemizde ve Çanakkale'de misafir etmekten onur duyacağımızı belirtmek isterim. Seminerin gerçekleşmesine katkı sağlayan Ekonometri bölümümüze, Mesut hocamıza, Merve hocamıza ve benim de çok kıymetli hocam Marmara Üniversitesi'nden Profesör Doktor Ebru Çağlayan hocamıza ve diğer fakültemizdeki personelimize çok teşekkür ediyorum. Seminerin katılımcılara yararlı olmasını dilerim.
Hocam çok teşekkür ederim. Thank you very much, Professor Sarıdoğan. Thank you for your efforts during this seminar process. So if this is okay, Professor, I would like to make a very brief introduction about Professor Lee. So Professor Lee, he received a bachelor degree in economics from the Seoul National University in 1983. He received a master degree in economics from the State University of IVE, which is located in the United States in 1986. He then received a PhD degree in economics from the University of Wisconsin-Madison in 1989. So Professor Lee worked at different universities around the world. He worked as an assistant professor at Pennsylvania State University, at Tilburg University and Tsukuba University, Xingyunwan University, Singapore Management University, Chinese University of Hong Kong, Australian National University, and he's currently working at Korea University, which I mentioned at the very beginning of my speech. Professor Lee has valuable contributions to the econometrics literature, and he has been ranked among the top 100 scientists in the field of econometrics many times. Since 2011, he has been designated a distinguished author by the Journal of Applied Econometrics, and he has been a fellow of the Journal of Econometrics since 2012. He has many published articles, books, chapters in econometrics. His main research fields are semi-parametrics, non-parametrics, panel data, limited dependent variable, sample selection, treatment effects, and duration analysis. Professor Lee, it's a very great honor for us to have you here. And the title of today's seminar is How to Apply OLS and IVE to Any Outcome Variable. And the floor is yours, Professor Lee. Thank you very much.
Well, thank you very much for the nice introduction. I hope all of you to go back to your place learning something new today. Let me start by saying that despite a lot of advances made in econometrics, many people still just use linear model and then OLS and IVE. This happens in private industries such as consulting firms, investment banks, but also you can see articles in top journals. They apply OLS or IVE to linear models, despite that their outcome variable is, for example, binary. As a fact, we know that if outcome variable is binary, then a linear model does not hold in general. So the big question that I always had in mind up to actually this point is that, I mean, what do we actually estimate if we apply OLS or IVE to linear model where the outcome variable is not continuous? There are many non-continuous outcome variables, and today I will just look at binary outcome just as a primary example. Okay, but what I present today, it actually apply to any form of outcome variable. So I had this question a long time ago when I just started majoring in econometrics, and the answer has been elusive for many years, and now I just have the complete answer, which I'll present today. If you look at this kind of linear model, that is binary treatment, and X is what we call covariates. Okay, regressors, they are not of primary interest. Okay, so this is the regressor of primary interest. U is an error term orthogonal to treatment and covariates. And if you look at this model, slope of D, namely the effect of D, is assumed to be a constant. But if you think about recent COVID experiences, you can easily see that with treatment being a COVID vaccine, you can easily see how diverse, how heterogeneous the COVID vaccine effect is. Okay, I believe treatment effect is almost always heterogeneous. Okay, and it hardly ever it will be a constant. And yet we frequently use a model like this with constant treatment effect. So the main question is, if the treatment effect is unknown function of covariate X, then what do we actually estimate with the OLS? To provide an answer to that question, let's define propensity score, PS. I'm using pi for P. So pi sub X is as well known as conditional mean of treatment given X. Angrist and Pischke in this popular book, Mostly Harmless Econometrics, they show that OLS slope is consistent for a weighted average of the unknown heterogeneous effect, where the weight takes this particular form. The weight is proportional to the conditional variance of the treatment given X. Since D is binary, this conditional variance is equal to the probability of treatment being 1 times probability of treatment being 0. So this is the well-known answer to the critical question. However, this answer requires a restriction that is conditional mean of d given x, namely the propensity score, is equal to the linear projection of treatment given x. Linear projection is defined like this. And if you look at this definition of linear projection, you can actually see that this is nothing but population version of the OLS predicted value of d given x, because this is the OLS parameter, and that is multiplied by x. So this is nothing but predicted formula in the OLS. So simple way just to appreciate this restriction is that linear projection is a linear function of x. You see, this part is a constant. So linear projection is always a linear function of x. But a conditional mean, it can be anything. It can be easily a non-linear function of x. So you can see how restrictive this condition is. One well-known sufficient condition for this restriction is that the model is saturated, by which I mean x is discrete, and we use a full set of dummy variables for all possible values of x. So we have such a model, then this restriction holds. But as you can see, in reality, this is not going to hold in general. So that brings up the question back again: what does this OLS estimate? Estimate when true effect is heterogeneous? To answer that, the key equation is what I called linear in treatment representation. For that, let's look at potential outcomes for treatment 0 and 1. Okay, this is well used, frequently used notation. There are many examples for this. I mean, if the treatment is college education and outcome is lifetime income, this Y0 will be lifetime income without college education, and Y1 will be lifetime income with college education. And for each individual, we can observe only one of these two. Okay, you either go to college or you don't. Okay, you do not observe both for each individual. Now let me make a typical exogeneity assumption of the treatment in this form, that given x, d is independent of potential outcomes. In randomized experiments, as in medical science, we assume that d is simply independent of potential outcomes. But in observational data, that hardly ever happens. However, if x is quite detailed, then controlling those x, we may assume treatment is as good as randomized for potential outcomes. And that's what this assumption requires. Observed outcome can be written in this way. So when t is equal to 0, y is y0. When t is equal to 1, y0 here is cancelled by y0 here, and y is equal to y1. This is almost a definitional equation. Okay, depending on the person is goes to college or not. If it does, we observe y1. If it does not, then we observe y0. So on this equation, we take this conditional mean. That will give me this line. As you can see, these conditional means appear. Since this in the conditioning set, this D is gets split from this due to the exogeneity assumption. Okay. That's what I have. Yeah, and since this in the conditioning set, we have the conditional mean on this is equal to this, then we invoke this assumption so that D drops out of the conditioning set. So first term becomes simply y0 given x expectation. That is defined as mu0x, and also slope becomes y1 minus y0 given x, that we define as mu d x. So I can rewrite this equation into this. And finally, I define error term as y minus this conditional mean. And then I put this on the left-hand side and u on the right-hand side. And that will give me this. And I substitute this equation into here and put u on the right-hand side. So that gives me this nice linear in D representation. And by construction, I mean, because due to this definition, U is conditional mean of U given D and X is equal to 0. This is not something I invented. I mean, many people in the treatment effect analysis field, they have known this equation. And this holds always as long as y1 minus y0 makes sense. Okay. This difference makes sense for continuous variables, count variables, also binary variables. I mean, when y is binary, you can see that this is what people call a marginal effect, right? If you use say data, it almost always shows you the marginal effect when y is binary. So for binary y, this certainly makes sense. If y is categorical, then this does not make sense. So what you can do then, you define a binary variable for each category. And if you use them, then y1 minus y0 will make sense. So what is nice about this equation is that this is linear in D, and it holds for almost any form of outcome variable. You see, people using a linear probability model, that is this linear model for binary y, they somehow thought about justifying this linear model by, for example, if the true model is Prof, you can imagine that this standard normal CDF being almost linear when the argument is around 0.5. So people thought about linear probability model in this way, namely approximating this nonlinear function with a linear function. If y is count variable, then exponential regression function is frequently used. There people thought about approximating exponential function, which is obviously nonlinear, with a linear function. Okay, but this way of thinking is not really fruitful. I think it's much better to look at this. I mean, this way of bringing treatment variable into a linear form instead of, the traditional way of thinking, as these terms show. So we have we can call this a true model because this holds almost always. We can call this true model. So what I'm going to do is that I'm going to substitute this true model to the OLS formula to estimate the slope. If I do that, that will show me what I actually estimate with the OLS when the treatment effect is heterogeneous. Before I do that, let me point out why the restrictive condition right here was used in the literature. The way people approach the problem is the so-called partial regression. So when you have a linear model like this, you take a linear projection given x on this model. You see, linear projection has several properties similar to those in conditional mean. So you can pretend as if this is conditional mean, and you take this on this, then you get linear projection of y given x, and this comes out as such, a linear projection of t given x, and linear projection of error term given x is 0. Okay, because this is also, has conditional mean 0. This is orthogonal to x. So after getting this equation, you subtract this from original linear model, and then dependent variable becomes this, and this x part drops out in the subtraction. So d part becomes this, and u it comes here. So this is again a linear model, and we apply OLS of this new outcome variable on this new treatment variable. And OLS takes this form, right? The regressor squared expected value in the denominator, and then covariance between the regressor and the outcome dependent variable. This is the nothing but the OLS formula, but it looks a little complicated. Then we see that this linear projection of y given x, it drops out because this projection residual is orthogonal to any linear function of x. And since L of y given x is linear function of x, it is orthogonal to this, so we can remove this part. So that gives a much simpler expression like here. Now, this is simpler, but it has a problem because there is expected value outside, and inside you have a linear projection appearing. So this is hard to interpret. that prompted people to replace this L with expected value under this assumption. So making this assumption, you replace linear projection with propensity score. So that then you get this this part. Now I substitute true model of y into this formula. By true model of y, I mean this model. So if I substitute that equation, oh yeah, it's right here. Then only thing that remains is this part, because this residual is orthogonal to any function of x, also orthogonal to u. Okay. So when I substitute this equation to this y, u drops out, the intercept drops out, and only thing that remains is this part. And this part can be rewritten as this. That's this expression. So you may be wondering how just a second, this becomes this weighted average. So let me show a little detail. Although, I mean, if you, you don't have to actually follow this derivation. I'm just showing how the last line holds. So as written here, this equation was substituted to this y. And then that gives this expression. Let me explain how that happens. First, this part is y. And then I said this intercept part drops out, arrow term drops out to leave only mu dx times t, that is here. Okay. And from this expression, I subtract this. This is actually 0 because t minus ps propensity score is orthogonal to any function of x, and this is entirely just a function of x. So subtracting this from here does not make any change. So that gives me this. And from this point, you can see that the two terms share d minus ps and also this mu dx. So if I factor them out, then I get the next line. The next line now finally is rewritten in this form, and that is the weighted average of heterogeneous effect. Now, let me introduce a name for the weight. This weight is called overlap weight, OW. This weight appeared in these papers under the assumption that conditional mean is same as linear projection. Let me point out just some primary advantages of this overlap weight. First of all, you can see that this is a quadratic function of PS, propensity score. And if you plot this as a function of PS, it attains a maximum in the middle when PS is 0.5. and it is 0 when PS is 0 or 1. So simply put, the maximum weight is given to individuals close to being randomized in this sense. If you think of PS matching, that is quite popular among applied researchers. If somebody has PS 0.5, it's fairly easy to find the matched subject in the opposite group. But if the person has PS too small or too large, then it gets difficult to find matched subjects in the opposite group. So OW rewards good overlaps while penalizing poor overlaps. Okay. So in practice, when you use PS matching, what people do, they simply drop out, they simply remove individuals who are not well matched. That is, if somebody has PS too small, too large, you just remove those individuals from your study. And formally speaking, removing those subjects is same as using weight average, where the weighting function takes value 1 in the center and value 0 near the two tails. And the weight is like it's like uniform weight, okay? It's like this head shaped, okay? It's highly non-smooth weight, okay? If you are familiar with non-parametric regression, you would know kernel non-parametric regression. Okay, kernel is a weighting scheme. So you can easily imagine, instead of using uniform weight, you use a smoothed version. Okay, if you smooth uniform weight or step-shaped weight once, then you get piecewise linear weight that looks like a tent. Okay, and tent-shaped weight, it also reaches maximum at 0.5 and minimum at 0 or 1, but it is still non-smooth at this point, at this center point. So you can go one step further by using quadratic weight. And this OW is nothing but such a quadratic weight, okay? That's twice smoothed version of a step-shaped uniform weight that is used in PSM. Okay, so at this point, let me just remind you that overlap weight is not something highly artificial, okay?
Sorry, Professor, I guess your microphone, we can't hear your voice.
Slides now?
Yeah.
Okay.
Yeah.
So anyway, let me know if that problem
Sure.
occurs again.
Sure, Professor, thank you.
So let me repeat what I said, that OW is not something artificial. It occurs naturally in linear models when you apply partial regression to focus on the slope of the treatment. Okay. When you do that, you get this expression, but then it's awkward to have L and E at the same time. So people impose this assumption to have this expression. And this expression, it leads to overlap weight straightforward. And I mentioned the primary advantage of OW, rewarding good overlaps and penalizing poor overlaps in, say, PS matching. Let me talk a little more about OW advantages. You see, this expression on top is the usual effect on the population. It is an integrated version, averaged version of this heterogeneous effect, where the distribution of X is used as the weight. Okay. But if you use this, the following problem occurs. This well-known #1 tennis player in the world, this guy Djokovic, he staunchly refuses to get vaccinated. Okay. For such a person, it is pointless to talk about this treatment effect because he will never change his treatment status. And suppose, say, 5% of the population are like him. They never get vaccinated. But in this definition, those 5% will appear. Okay? That's what I mean by a poor marginal effect. Okay? Those individuals should be better be excluded from the definition of treatment effect. And you can also think of the opposite group who always get vaccinated no matter what. And also for them, including them in this definition of treatment effect would not be a good idea. So excluding them is done automatically in OW by assigning a low weight to those individuals. So that's one advantage. Another is that although many people use PSM, in the treatment effect literature, possibly the second most popular estimator is IPW, inverse probability weighting. The canonical form of IPW is same as this, except OW replaced by 1. So let's imagine this does not exist for a while. Then you get IPW estimator. If you look at this expression here, when D is multiplied to Y, Y becomes Y1. And when 1 minus D gets multiplied to Y, Y becomes Y0. So that gives me this expression right here. Why does this expression appear here? And also why does this expression appear here? That's because to cancel out the numerators, okay? So the function of D here is to turn Y into Y1, and the function of D is to turn this to Y0. But then you have to get rid of D and 1 minus T, which is done by these two denominators. So that's IPW. It's a very simple, attractive idea. In fact, when I teach my treatment effect course, when I mention IPW, then my students always complain. I mean, why didn't you teach this simple, elegant method in the beginning instead of messy PS matching? The reason is this IPW has a critical problem that it does not work well when the denominators are close to 0. Okay, you can imagine denominators being 0.00001. Okay, the whole thing can blow up. So instead of the usual IPW that is consistent for this, if you multiply overlap weight here, you will be estimating this overlap weighted effect, tau W. You can immediately see the benefit because this will cancel out this PS, and this will cancel out this denominator. So the IPW will become numerically stable. So PSM is probably most popular, and second most popular would be IPW. The third approach will be what they call regression imputation or regression adjustment. That looks like this line here. Again, let's imagine this part, overlap weight part, non-existent for a while. So what people do in regression imputation, they estimate this term and this term separately, and they plug in the estimators here to finally estimate this effect on population. How do I estimate these things? Well, you obtain, you estimate PS, and this can be approximated as a polynomial function of PS for the treatment group. And this part can be approximated with a polynomial function of PS for the control group. So you plug those estimates into this formula, and finally then you get this. Even in this approach, where there is no troublesome denominator, if you multiply OW here, then amazingly, any misspecification in these two functions does not matter anymore. I mean, when you do approximations here, you worry about misspecifications in those approximations, but when this appears here, your estimate becomes robust to such misspecifications.
And Professor Lee, would it be okay to ask a very small question here at this point?
Sure. Go ahead.
We actually had a chat with Professor Charlan about this regression imputation, and we were actually wondering whether is it quite similar to the standard imputation techniques that we use when there is like there is the issue of missing data. I mean, can we use any kind of imputation technique here at this very moment? Because we say the PS-based imputation. So can we use any imputation technique? We had a chat on this with Professor Charlan. So when I see the slides, I say, okay, this is where we were stuck.
You say that people use this term imputation in that context when you're missing variable, right?
Yeah,
missing values.
Yeah.
So if you think of this as a missing value, you can use the term. In fact, this finding was first noted in this paper. This stands for Statistics in Medicine.
Yes, Statistics in Medicine.
As I recall, they talk about some imputation issues in the paper, not just treatment effect. So maybe the best thing to do is to look at this paper.
Sure. It's usually the case with the health data, isn't it? I mean, there is like a majority of the data would be missing. This is usually the case in the health data, especially in microeconometrics. So thank you very much. We will check the paper. Thank you.
So off the top of my head, I mean, probably I can think of imputing missing value with some X conditional means.
Yeah.
And then if you are concerned about misspecifying X conditional mean, then if you use OWs, that problem will be mitigated. That's how I mean.
Yeah,
that's my own imagination of how things would go.
Sure. Thank you very much.
Yeah. So this is not statistics in medicine. Is not a highly technical journal. So I think it's not going to be difficult to read this paper. By the way, I think there is some errors, not serious, some minor errors in this paper when they prove this. So I have a review paper of OW weight in this paper this year. This is Journal of Statistical Planning and Inference. And there, I think I corrected some minor errors in this paper. Okay, so those are advantages, and there is another advantage that is relatively minor. So I'll skip the number 4 here. Oh, next slide is that it's just a proof. The conditional mean being equal to linear projection. I said that holds for saturated model, and this entire page proves this claim. This is not highly difficult, but proof is not easily seen. So I decided to add one-page proof in case somebody is interested in seeing the proof. Okay. Now, let me go back to the very first question today that I raised. If you apply OLS to linear model when outcome variable is binary, you don't know what you're estimating. But if you assume that linear projection is same as PS, then you get to estimate overlap weighted average. So the main question is, so without this restriction that a linear projection now defined as lambda x, without assuming lambda x is equal to pi x, then what does OLS estimate? That question is here. If you apply OLS, you estimate some weighted average plus some bias, okay? But this particular weight, which I dubbed omega mix, it does not make a lot of sense. If you look at this formula, first part is OW, which makes good sense. The second part, it does not make sense because it reveals the discrepancy between propensity score and linear projection. I cannot think of any reason why individuals with high discrepancy should be given high weight. Plus this bias term that's presented here. If you look at this bias term, if PS is equal to linear projection, bias becomes 0. Now suppose PS is not the same as linear projection, and let's assume this effect is 0. You can see that when this effect is 0, as long as PS is not the same as linear projection, in general, the bias does not drop out. So that gives the conclusion that the simple OLS to linear model for binary outcome is not consistent in the sense that even when this effect is 0 for X, this bias does not drop out. Okay, so only way the OLS to make sense is assuming this critical assumption that linear projection is same as PS. But then I already mentioned that's not going to happen often in reality. So that leads us to the next question. Is there any way to estimate then this overlap-weighted effect without the critical restriction? That estimator actually does exist. The simple thing to do is just OLS of Y on D minus PS. If you do that, you get a consistent estimator for overlap-weighted effect. And this procedure does not need the critical assumption. You see, if you recall why we imposed this, the reason was that linear projection appeared in this place, which people did not like. That's why they imposed this. Then why we can just start we can just use D minus PS, and doing so we can get rid of this restrictive assumption. So this is the idea, or simple idea, why OLS of Y given Y on propensity score residual. Okay. In fact, this idea, this OLS was proposed long time ago by Robbins and others. This is about 30 years ago. But they looked at only continuous outcome Y, and they considered so-called partially linear model of this form. Okay, so here you can see that the constant effect appearing again, and the model is partially linear because the intercept is unknown function of X. So let me denote this OLS as OLS PSR. So main advantage of OLS PSR is simplicity. It is consistent to this overlap-weighted effect for any form of Y and for the unknown heterogeneous effect. So we are not directly estimating this unknown function of X. In implementing this OLS PSR, I actually used Y minus the conditional mean of Y given PS instead of simple Y. Using this, it doesn't matter in terms of population, because this extra term is orthogonal to this, so it'll drop anyway. But then why am I using this? The reason is if I used this centered outcome variable, then the procedure becomes more robust to misspecified PS. Here I use term double orthogonalized, and I'll explain this term later near the end of my seminar when I talk about machine learning in causal analysis. Okay, how do I implement this? You can easily imagine that this PS can be replaced by probit or logit. And this part, for example, I do probit to estimate the probit regression function. Then I make power functions of the probit regression function. I do OLS Y on these power functions to get the estimates. Then I can construct sample version of this conditional mean using the probit regression function power function, and this estimates. Instead of this probit regression power functions, I can also use PS to the power of 0 all the way PS to the power of Q. They are equivalent, but there are pros and cons in using this versus using power functions of PS. So I'm just presenting this version for simplicity. By the way, this double orthogonalization is a nice feature to have. It gives robustness to specified nuisance functions such as propensco. To be fully double orthogonalized, I should use y minus conditional mean of y given x. But then using this would be impractical. I mean, when x is high dimensional, using this is not advised. That's why I'm using this to reduce the conditioning dimension down to 1. Okay, whereas still being close to double orthogonalization. Now, some people simply just downright refuse to use anything other than linear model. Okay. If you insist on using only linear model, you see, going back, OWPSR is not linear model. I mean, this is linear, but you have to do probit, right? So that step is a non-linear step. So if you do not want that, if you want to apply linear model like this, then what is the best way to proceed with this linear model? Here, somewhat surprisingly, the advice is that instead of trying to constructing the data generating process for outcome, you specify this X part to ensure that PS is close to a linear projection. What I mean by that is the following. Suppose your PS looks like this, probit with single regress X, then this is nonlinear function of X, whereas linear projection is a linear function of X. So to capture nonlinearity in X, you may want to use not just X, but X squared as well. Or even this capital phi of X. So instead of using X in this covariate part of outcome model, you use all of this here. Okay, that's far from DGP. Rather, it's close to what I just proposed. That is choosing the X part to make PS similar to a linear projection. You see, it's very tempting to think of in terms of DGP. Okay, but my suggestion is to resist that temptation, and you use the linear model such that covariate part in the linear model is going to make PS similar to linear projection. For that, let me introduce a dramatic example next. In this example, Y is the work or not in the current year. The current year is year 2000, and D is work or not in the previous year. So we are looking at the effect of working previous year on working on the current year. That is actually called state dependence in panel data setting. It matters greatly in marketing. If there is a strong state dependence, so if somebody consumes a product in 1 year, he or she will continue to consume the same product in the future. So in the work or not example, I can say strong dependence means once you work forever. Okay. So going back to this marketing example, if there is strong state dependence, marketing effort should be directed at initiating consumers into consuming that product. Once that happens, you don't have to spend any more money for advertising because the consumers will get hooked. You can, if you think of Coca-Cola or Starbucks, you probably understand what I mean. Okay. So in this particular example, covariates relevant to the treatment, they belong to the previous year, whereas covariates relevant to the outcome, it belongs to the current year. You see, normally in most examples, people take treatment when Y1 is greater than Y0, okay? So covariates affecting outcome is similar to covariates affecting the treatment. And there would not be much difference between the two sets of covariates. However, in this particular example, covariates relevant to the treatment, they are sharply different from covariates relevant to the outcome. And I picked this example to illustrate the dramatic difference between the two scenarios. So a table here for the Y outcome model and the treatment model, in number 1 panel, X0 is used. Okay, so X0 is for treatment. And number 2 panel, X1 is used for both. And X1 is actually close to YDGP. Okay. In panel 3, I use both. So you can see that the pseudo R-square in panel 1 is big for treatment, but very low for outcome, because the covariate explains treatment well, not outcome well. In number 2, the opposite happens. This R-square for treatment is low, whereas that for Y0, I mean the control group is very high. Finally, in panel 3, both covariates are high. But now let's look at the effects. In panel 1, effects are about 0.63 OLS PSR or 0.62. In panel 2, effects are much lower, 0.47, 0.46. And finally, in panel 3, when both are used, the effects are same as in panel 1. So this table reveals that using X1 is not critical. Rather, using X0 is critical. Okay. So as written here, in panel 1 and 3, you get to estimate overlap weighted effect, whereas in panel 2, you get to estimate this biased effect, which is much different from the effect in panel 1 and 3. So I hope this rather dramatic example convince you to set up your outcome model such that covariate in the outcome explains treatment well instead of outcome well. Okay. Now, so far I have been assuming exogenous treatment. Now, exogenous treatment, I mean, yeah, this is the treatment exogeneity condition, right? Now I relax this so that the independence does not hold. When treatment is endogenous, we need an instrument. Let's say we have a binary instrument Z for D. So you can think of D as a vaccine, and Z is an encouragement to get vaccinated. So D0 is the potential treatment without getting the encouragement, and D1 is getting vaccinated with the encouragement. In both cases, they can take 0 and 1. Okay. For a person like me, I will get vaccinated without or with the encouragement. So for me, this will be always 1. For somebody like Djokovic, he will never get vaccinated with or without encouragement. So for him, this will be 0, 0. We talk about compliers in this endogenous case. And compliers are called as such because their D0 is equal to 0, their D1 is equal to 1. So it looks like they are complying to the encouragement. In this endogenous case, it's much more difficult. But still, this linear in D representation holds. You see, we derived this on the treatment exogeneity. So that proof does not apply. So you have to do you have to prove quite differently for this. But anyway, the point is that this holds for endogenous D. But then identify the effect here is effect on compliers only. Okay? And also, please note that error term is orthogonal to instrument and X, not treatment and X. So using this, I proposed what I call instrumental residual estimator, IRE, where you do the usual single regress IVE, but the difference is that instead of using Z as the IVE, you use Z minus instrument score, defined as conditional mean of Z given X. And this includes OLS PSR as a special case when treatment is exogenous. This is shown to be the same as weighted average or this heterogeneous effect where weight is proportional to the covariance between instrument and treatment. You see, in the literature of IVE, people talk about weak instrument. Okay, so for those with high values of this, instrument is strong. So you can right away see that this weighting scheme makes sense because strong instrument people receive strong high weight. Okay, and in contrast, those with near zero covariance here, they receive a near zero weight. And this covariance can be shown to be equal to this. And you can see again overlap weight in terms of instrument score modified by complier probability. Okay, this extra term it comes because of the endogeneity. So if you want to apply IVE to this linear model, again, the advice is that do not try to construct DGP for Y. Rather, you set up this X part such that this conditional mean of instrument is same as linear projection for the instrument. Okay. So if you do that, you will get, even if you use IVE to this, still you are close to estimating this weighted average. Okay, that's pretty much the main story I wanted to convey today. And remaining three slides are about machine learning in causal analysis. I'll skip there are 3 slides left, but I'll skip second slide and talk only about first and the third. If you recall OLS PSR, you can see that there are 2 nuisance functions. One is PS, and the other is this expected value of Y given PS. They are called nuisance functions because you are not interested in them, but they have to be estimated in order to find treatment effect. Okay. So the people have been concerned misspecify nuisance functions. In the literature, there is something called double robustness, DR. It means that your estimator is consistent if one function is correctly specified, if either one function is correctly specified. Okay. So in specifying these 2, if either one is correct, then no matter how wrong the other function is, still your final effect estimator will be consistent. That is called DR. But it is not a local property. Rather, it's a global property. In reality, our specification would not be exactly correct, but neither grossly wrong. What is more likely in reality is that both are close to the true function, but not exactly equal. Okay, so we need local robustness property rather than global ones such as DR. And one example for a local robustness is the double debiasing or double orthogonalization. Here I abbreviate as DDB. And this idea can be seen in Econometrics Journal 2018. And just last year, Econometrica published a couple of papers, I think like 3 papers on this DDB. OLS PSR is not DR, but if I use, as I already mentioned, this Y minus X conditional mean as the outcome variable, then OLS PSR becomes DDB. Just to give you intuition why using this gives a DDB property, let's look at this moment condition defining OLS PSR. You see, in this moment condition, outcome variable is centered, conditionally centered, and treatment variable is also conditionally centered. So we are doing double centering or double debiasing. And setting this moment equal to 0, if I solve this condition for t, you can see that the outcome is multiplied by this regressor, and this regressor is multiplied to this regressor. So if you solve this equation for t, what you obtain is this, where this conditional mean is replaced by this conditional mean. Okay. If you differentiate this moment condition with respect to this nuisance function and this nuisance function, you can actually see that the derivative becomes 0. And the fact that derivative is 0 gives local robustness. This explains why using the conditional mean of y given PS is actually not enough, because if you use that, the derivative, one derivative is not equal to 0. And that is explained in second slide here, but I'll skip that part. Let me just mention some expressions for double the biasness. Suppose you use a moment condition like this. If in this moment condition, this psi will have nuisance functions, and you can imagine differentiating this with respect to the nuisance functions and checking out derivatives. If those are 0, then this function is called Neyman orthogonal. Okay. For the second bullet point, let me go back to the regression imputation idea. Yeah, here is the regression imputation idea. You can imagine this overlap being non-existent. So in this regression imputation idea, there are two nuisance functions, first one and second. Okay. As such, this moment condition is not double debiased. So what you can do then, you add some correction term to this moment condition to turn to get DDB property. Okay. Let me call this row 1 and this row 0. Okay. So row 1x and row 0x. So if I use this will be regression imputation estimation with these nuisance parameters. And in this case, this does not have DDB property. So you can add some terms, which I call correction terms, to turn this into another moment condition with Neyman orthogonal function psi. So trick is how to find those correction terms. They can actually find, they can be found in this paper. Essentially, you have to figure out how the nuisance functions, such as this, nuisance function estimation affects your final treatment effect estimator. So as written here, for example, if initial moment function psi 0 is a score function over likelihood, then Neyman orthogonal psi is the efficient influence function to estimate this. The original paper of this 2018 Econometrics Journal or last year Econometrica, they are quite difficult to read. So if you want to start, maybe this AER papers and proceedings 2017, it is much easier to read. The reason I'm mentioning this double D biasness is that myself, I thought machine learning has no place in causal analysis until recently. The reason was that, for example, I mean, it's suppose going back to this regression imputation. I mean, I can plug in machine estimated nuisance functions here. That'll give me my treatment effect estimator. But the problem is, it's very difficult to account for the estimation error when machine learning is used in the first stage. Okay, but that was main obstacle in applying machine learning methods in treatment effect analysis. If you think of two-stage OLS, in the two-stage OLS, the first step is conditional mean of endogenous regressor on the system exogenous regressors. That can be also estimated by machine learning. But then the same problem occurs. I mean, how to account for first stage estimate error on the final stage. Whenever we make use of reduced form estimate, we can always use machine learning technique. By reduced form, I mean we use predicted value, not the parameters that gives you the predicted value. In the case of two-stage OLS, first stage is OLS of endogenous regressors on exogenous regressors, but we use only the predicted values. We are not looking at individual slopes of first stage OLS. And there are many such reduced forms. I mean, in regression imputation, these are such reduced forms. For OLS PSR, this propensity score is also reduced form. I mean, reduced form estimation problem. So because of the problem, I was kind of pessimistic of applying machine learning to causal analysis. But what this paper showed is that if you use what they call cross-fitting or cross-validation, then first stage error can be ignored. That's actually an amazing result. So what they do in cross-fitting is that they divide the sample set into 5 groups, and they use first 4 groups to estimate the reduced form. And using the predicted value of the reduced form, they estimate treatment effect in the last 1/5 of the sample. Okay. So that can be done once, and then you can take turn by regrouping the subsamples. That's what they call cross-fitting. So if you do that, amazingly, estimation error in the first machine learning stage can be ignored. So you can see that machine learning will be used more and more. Okay. Yeah. That's, I guess, all I have to say.
Thank you very much, Professor, and thank you very much for helping us be aware of this particular method. Would it be okay to take any questions or comments? Are there any questions or comments from the floor? Any questions or any comments? You can even ask in Turkish. Türkçe'de sorabilirsiniz, hocamıza iletebiliriz.
Hello, I am Zeynep. I am working as a research assistant at the Department of Ekonometri. Thank you, Professor Lee. Such an interesting and excellent seminar.
Zeynep, she's working as a research assistant at the Department of Econometrics in our department. So she's speaking at the moment, I guess. Yeah. Any other questions or any other comments?
Oh, by the way, I just early this year I ran into this book, which is an edited volume from Springer. Its book title is Econometrics and Machine Learning. So it's an edited volume. It goes over how machine learning is used.
Exactly.
And there is one chapter in that book on causal analysis and machine learning. And they talk about two main areas where machine learning is used in causal analysis. One is double debiasing, as I explained today, and the other was treatment effect heterogeneity. You see, in today's talk, I did not actually estimate heterogeneous effect, okay? I just estimated one weighted average of that, right?
Yeah.
But now some people, actually many people try to estimate this heterogeneous effect function itself.
Mm-hmm.
And by doing so, you can kind of, you can tailor each treatment to each individual, okay? To each individual's characteristic. So there's two main areas where in causal analysis where machine learning is used at current time. Okay.
Professor, some of my students were texting me, they're emailing me at the moment, and they're asking whether they can directly apply or imply this method on any package programs or any softwares like R.
No.
Or are you working on this?
No. As I said, if you directly simply apply machine learning in the first stage,
then
in general, the machine learning first stage estimation error matters. So instead of applying directly, you have to modify your moment condition.
Yeah, I see.
In a way I described in my last couple of slides. If you do that, then you can apply without worrying about a first stage estimation error. Yeah. The papers I mentioned, they give several examples, but actually, unfortunately, the papers are quite hard to read. So the 2017 paper in AERPP, or this edited volume published last year in Springer, may help the students if they are interested in this topic. Yeah.
I will let them know. Thank you very much, Professor. Kıymetli hocalarım, kıymetli dekan hocam, kıymetli Ebru hocam, kıymetli tüm hocalarım, kıymetli katılımcılarım. Ben sözü size devretmek isterim, kıymetli dekan hocam.
Ben de tekrar profesörlüğe...
Please go ahead.
Ben de kıymetli profesörlüğe katkılar için çok teşekkür ediyorum. Aynı şekilde Merve hocam size, Ebru hocam sizlere de çok teşekkür ediyorum. Böyle bir teorik konuda da katılımcılarımız sabırla 41 kişiyle başlamıştık. Bir 62'ye yükseldi ama teorik konuya rağmen sabırla dinledikleri için onlara da teşekkür ediyorum. Gelecek seferlerde uygulamalı konularda daha da büyük talep olacağını tahmin ediyorum.
Çok
teşekkürler.
So our dean, he would like to thank to you and thank to all guests and all academics who are with us at the moment. Hocam, Ebru hocam bir şey söylemek ister misiniz?
It was very pleasure to listen again. Thank you very much, Professor Lee. See you tomorrow.
Okay. All right. Thank you for attending this seminar. I'll see you someday.
It was a pleasure.
Thank you very much, Professor. Thank you very much. We are really grateful for the time you spent for this presentation for the faculty and the department seminar series. And thank you everyone for attending. I think this is all for now. We would like to see you in our next seminar. Professor, thank you very much. Thank you.
Okay. Bye-bye.
Bye-bye. Thank you.
Bye.